All right, everyone. In this video, we're going to talk about solving systems of equations, linear equations, by substitution. We just spent a couple of class days solving by graphing. This time, we don't have any graphs. Not every equation is going to be in slope-intercept form. So we need to talk about how to substitute. You guys know, for the most part, how to substitute a value into an equation, but now we're going to be replacing variables with more than just numbers. So when we substitute, we can replace, not the variable, a variable, with a number, which we know how to do, or an expression. And this is the new part. So what I mean by subbing in an expression is instead of just subbing in 3, you might sub in like 2x or 3x plus 5, something similar to that. So this says solve each system using the substitution method. In the first example, you're told that you have 3x plus y, and then you're told that y equals 3. I can just replace the y in the first equation, with what y equals, which is 3. So I have 3x plus, instead of y, I'm substituting in 3, equals 15. And then solve your equation using the steps, that's 12, that we have been using since the beginning of the year. I get x equals 4. So my solution is 4, 3, because it's alphabetical order, x, y. That you guys know how to do. 2 is where things get a little more interesting. Instead of just having j equal to 2, we have j equal to 2k. This is what I mean by subbing in an expression rather than just a number. So I'm going to take what j equals, which is 2k, and substitute it in for j, the same way I did before with the 3. So instead of j, I'm going to replace it with 2k, and everything else in this problem stays the same. Sorry that every time I pick a color, it covers up the work. So I have 2k plus 3k equals 5. Combine like terms to get 5k. Divide by 5. K equals 1. The whole point of doing this is so that we can eliminate one variable and just work with another. So I'm replacing j so that I only have k's in this problem. I'm not done. Since I have k, I now need to find out what j is. So I substitute back into either equation. I'm going to pick the first one because it's already in the form of j equals. So I'm going to have j equals 2 times, k is 1, so sub in 1. I get j equals 2. My solution in alphabetical order is 2, 1. The same way that we checked our solution with graphing, you need to check your solution with substitution by substituting back into both of the original equations. I stress that because if you make a mistake and you don't sub it in properly to check, you're not going to know if you're wrong. So I'm going to have 2 equals 2 times 1, 2 equals 2. That's a true statement, so I know that's correct. And then in my second equation, I'm going to have 2 plus 3k equals, what's k? K is 1. Remember, we usually use parentheses when we substitute. 2 plus 3 equals 5. 5 equals 5. And just to show you specifically, I'm substituting into this equation that I was given. And for this one, I was substituting into j equals 2k. So these both work, so I know that my solution is correct, 2, 1, and I can move on. It's a little dark. I don't know why. I don't know what just happened to the brightness, guys. So now I'm going to substitute something that has more than one term, which means there's a plus or minus sign involved in what I'm substituting. So my given equation, the first one is 6m minus n equals 5, and the second equation is n equals m plus 5. Since I have n equals, I can replace the n in the first equation with what it equals. Please remember, use parentheses when you substitute. So everything stays the same except for the n. Instead of the n, I know that it's equal to m plus 5. And you guys know how to solve this. I need to distribute that negative, combine like terms, add the constant, and divide by the coefficient. So m equals 2. I have half of my solution. To find the other half, I take that and I substitute it back into what n was equal to. So I knew n was equal to m plus 5. I know that m is 2. So n equals 7. So I get my solution is 2 comma 7. To make sure that's correct, I have to check it in both of the original equations. So I'm going to use the 6m minus n equals 5. And if I do that, I have 6 times 2 minus 7 should equal 5. So I get 5 equals 5. That one's good. And then the second one I'm going to check is in n equals m plus 5. So I'm going to sub 7 equals 2 plus 5. 7 equals 7. So I know my solution is correct. The last example is the most difficult, but probably the most common that we'll work with for the rest of this unit in both solving systems using substitution and with our next type of method, which is elimination. Both of these equations are in standard form. Neither of them are solved for a variable. So I don't have a variable by itself. I don't have anything like y equals mx plus b. I don't have anything that says x equals whatever it equals. So my first step is going to be to rearrange one of the equations for a variable, or to equal a variable. Usually you're going to try to solve one equation for x or y. Those are the most common variables we use. You don't always want to solve for y. Sometimes it's more difficult to solve for y. So if I look at the first equation I'm given here, x minus 3y equals 9, I can actually really easily solve that for x because x doesn't have a coefficient. So I can just add 3y to both sides, and in one step, I have that x equals 3y plus 9. I can now use that, again with these colors, I can then use that and sub it into the second equation that I'm given in my system, which is 6x minus 5y equals 2. So I can take my x and I'm going to put it up here for that x. So I had 6x minus 5y equals 2. I now have 6 times what x equals, which is 3y plus 9, minus 5y equals 2. Solve this. First step is to distribute. Combine like terms. I should have given myself more room on this problem. Okay, I'm going up here, so I've got 13y equals negative 52. Keep track of those negatives. I get y equals negative 4. So that's the first half of my solution. Remember, solutions are x comma y. So I'm going to fill in the y. In order to find the x, I want to take the variable I just solved for and substitute it back into one of the original equations. It doesn't matter which one, whichever one you think is easier. Again, always go back to the original. That way, if you make a mistake somewhere, you're gonna find it when you check. So I'm gonna take the y equals -4 and sub it in for the y into the one of the original equations. Double negative makes a positive. Subtract from both sides. X equals -3. So my solution is hopefully correct, -3, -4. I'm going to check that real quick. I encourage you to check it on your own. You guys should know how to check by now since we were doing it in the graphing method. So quickly I'm going to have -3 minus 3. Oh, let me show you which one I'm checking in. So I'm checking in the first equation first. So I'm just going to sub in x and y. Make sure it works out. I get 9 equals 9, so the first one is good. I gotta make sure I check them both, so 6x minus 5y equals 2. Replace the x and the y here, so I'm gonna have 6 times -3 minus 5 times -4 equals 2. -18 plus 20 equals 2. 2 equals 2. I get a true statement, so I know that my solution is correct. There's a lot of steps that go into solving by substitution, but if you use colors or highlighters, arrows, it all makes sense as long as you stay organized. And that's it, solving by substitution.